The next part is the binomial distribution. Now if we consider n independent trials, then the probability of A happening or the success of A is equal to P, and the probability of A not happening, that is the failure of A, is equal to Q. Let us say that this is equal to P and this is equal to Q. Then P plus Q would be equal to 1, as these are mutually exclusive events, and so Q would be equal to 1 minus P. Now if we say that X is the number of times A occurs, that is X represents the number of times A happens, or it represents the success of A, then X is greater or equal to 0 and less than equal to n. Here n is the independent number of trials. So if we consider n independent number of trials, then the number of successes of A would be X, and this X lies between 0 and n, and P is the probability that A happens and Q is the failure of A. Now X equal to R means that A occurs in R trials, and in the remaining n minus R trials it does not occur. So it may look like A up to R times it's happening, and in the remaining n minus R times it's not happening. So it should be represented by A complement. So A till R times and A complement to n minus R times represents one outcome in n trials. Now the trials are independent of each other, that is they do not influence each other. Hence the probability would be P into P into P up to R times into Q into Q into Q up to n minus R times, and this would be equal to P to the power of R into Q to the power of n minus R. Now we see that these could be arranged among themselves in NCR ways. Hence we can say that the probability of getting R successes or occurrence of A in R trials out of n independent trials is P of X equal to R equal to NCR into P to the power of R into Q to the power of n minus R. And this is the binomial distribution of the random variable X. Now X could be 1, 2, 3, 4 up to n. So in general, if A occurs R times, then X is equal to R, and so the probability distribution would be NCR into P to the power of R into Q to the power of n minus R. Here we should note that each of these n trials are independent of each other, and the probability of occurrence of A in one trial is P, and the non-occurrence of A is represented by Q. So P of X equal to R is given by NCR into P to the power of R into Q to the power of n minus R. Now let's see some of the very important results regarding the binomial distribution. The first is the probability of getting at least k successes is P of X greater or equal to k, and which is equal to the summation of NCR into P to the power of R into Q to the power of n minus R, where R varies from k to n. Thus, if we want to calculate the probability of at least k successes, here the random variable varies from k to n. So this would be equal to the summation of NCR into P to the power of R into Q to the power of n minus R from R equal to k to n. The second is the probability of getting at most k successes is P of X less than equal to k, and this would be equal to summation of NCR into P to the power of R into Q to the power of n minus R, where R varies from 0 to k. So here for at most k successes, X would lie from 0 to k, and so it would be equal to summation of NCR into P to the power of R into Q to the power of n minus R from R equal to 0 to k. And the third is the summation of NCR into P to the power of R into Q to the power of n minus R from R equal to 0 to R equal to n is equal to P plus Q to the power of n, and we know that P plus Q is equal to 1, so this would be equal to 1. So this would represent the probability of the sample space. Thus these are some of the important results regarding the binomial distribution. Now let's see a solved example. A manufacturer of metal pistons finds that on the average 12% of his pistons are rejected because they are either oversized or undersized. What is the probability that a batch of 10 pistons will contain, option number A is no more than 2 rejects, and second part is at least 2 rejects. So in this problem it has been given that a manufacturer finds that on an average 12% of his pistons are rejected. This is because either they are oversized or undersized. Now what we have to do is we have to calculate the probability that a batch of 10 pistons will contain, first part is no more than 2 rejects and the B part is at least 2 rejects. So this is a case of binomial distribution, and so let us say that X is equal to the number of rejected pistons. Now in this case success would mean rejection. So if a piston is rejected, it means the success, that is the happening of that particular event. Now you're given that n is equal to 10 as we have got 10 trials. P would be equal to 0.12 as 12% of the pistons are rejected. Q would be equal to 0.88. Now let us say that it has got no rejects. So x would be equal to 0 and thus P of x would be equal to ncx into P to the power of x into Q to the power of n minus x. Now we see that x is equal to 0 here. So this would be equal to 10c0 into 0.12 to the power of 0 into 0.88 to the power of 10. This would be equal to 0.2785. For one reject, x would be equal to 1. So P of x would be equal to 10c1 into 0.12 to the power of 1 into 0.88 to the power of 9. So this would be equal to 0.37977. Now let's consider 2 rejects. So x would be equal to 2 and hence P of x would be 10c2 into 0.12 square into 0.88 to the power of 8, and this would be equal to 0.23304. Now we have to calculate the probability of getting no more than 2 rejects. So P of x should be less than equal to 2 and hence we add all these probabilities. And thus 0.2785 plus 0.37977 plus 0.23304 would be equal to 0.89131. Thus the probability of getting no more than 2 rejects is equal to 0.89131. The second part is we have to calculate the probability of at least 2 rejects. So for at least 2 rejects, this would be equal to 1 minus P of x less than equal to 1. So now P of x less than equal to 1 would be P of x0 plus P of x1, that is no reject plus 1 reject, and hence this would be equal to 1 minus summation of 0.2785 plus 0.37977, and this is equal to 0.34173. Thus this is the final answer for the probability of at least 2 rejects. Now this was all about probability. Now let's try to solve a few examples that have been asked in IIT JEE. So this problem appeared in IIT JEE 1989 and it says that suppose the probability for A to win a game against B is 0.4. If A has the option of playing either a best of 3 games or a best of 5 games match against B, which option should he choose so that the probability of winning the match is higher? No game ends in a draw. So in this problem it has been given that the probability of A to win a game against B is 0.4. Now A has got 2 options, either he can go for best of 3 games or best of 5 games against B. Now which option he has to choose so that the probability of his winning the match is higher? Also given that no game ends in a draw. Let us take the case first as best of 3 games. Let us say that A and B play best of 3 games. Now in this case, if A has to win, then he should win 2 or more games against B. So number of wins should be greater than equal to 2. Now if x is the number of wins, then n is equal to 3, that is they are playing 3 games. P would be equal to 0.4 as his probability of winning a game against B is 0.4 and Q is equal to 0.6. This is the probability of B winning against A. Now the probability of x greater or equal to 2 is equal to the probability of x equal to 2 plus the probability of x equal to 3. Now this is equal to 3c2 into 0.4 square into 0.6 plus 3c3 into 0.4 cube into 0.6 to the power of 0. This is equal to 0.288 and this is equal to 0.064. When we add them up, we get 0.352. If A and B play best of 3 games, then the probability of A winning is equal to 0.352. Let's take case number 2, that is best of 5 games. Now if we say that x is the number of wins, then n is equal to 5. Here the number of games is equal to 5. So n is equal to 5. P is again 0.4 and Q is equal to 0.6. So for A to win, we should at least win 3 games. So P of x greater or equal to 3 would be equal to P of x equal to 3 plus P of x equal to 4 plus P of x equal to 5. For this we get 5c3 into 0.4 cube into 0.6 square plus 5c4 into 0.4 to the power 4 into 0.6 plus 5c5 into 0.4 to the power of 5. This is equal to 0.2304. This is equal to 0.0768 and this is equal to 0.1024. And when we add them up, we get 0.3174. Thus we see that P of x in the first case is greater than P of x in the second case. That is, the probability of A winning against B in best of 3 games is higher as compared to winning in the best of 5 games. Thus A should opt for best of 3 games, as this gives him a better chance of winning against P. Let's try to solve one more example. This problem appeared in ITJ in 1997, and it says that if P and Q are chosen randomly from the set 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 with replacement, determine the probability that the roots of the equation x square plus px plus q equal to 0 are real. So in this problem we have been given that there is a set from 1 to 10 and we have to choose P and Q with replacement such that the roots of the equation x square plus px plus q equal to 0 are real. Now the given quadratic equation to us is x square plus px plus q equal to 0. Now we know that for roots to be real, the discriminant should be greater or equal to 0. That is, p square should be greater or equal to 4q. And for roots to be non-real, the condition is p square should be less than 4q. Now we know that the probability of roots to be real is equal to 1 minus the probability of roots to be non-real. So what we are going to do here is we are going to try to find the probability of roots to be non-real and then subtract this probability from 1 to get the probability of roots to be real. Now we also know that P and Q belong to the set 1 to 10. So we choose different values of Q from 1 to 10 and correspondingly we find the values of P. Thus, when Q is equal to 1, P would be equal to 1, and so the number of pairs of P and Q would be 1. When Q is equal to 2, the values P can assume are 1 and 2, and thus the number of pairs become 2. For Q equal to 3, P can have values 1, 2 and 3, and so the number of pairs is equal to 3. When Q is equal to 4, P can have values 1, 2 and 3, and so the number of pairs are 3. When Q is equal to 5, P can have the values 1, 2, 3 and 4, and thus the number of pairs are 4. When Q is equal to 6, P can have the values 1, 2, 3 and 4, and hence the number of pairs is equal to 4. When Q is equal to 7, P can have 1, 2, 3, 4 and 5, and so number of pairs is equal to 5. When Q is equal to 8, P can have the values 1, 2, 3, 4 and 5, and hence again the number of pairs are 5. When Q is equal to 9, P can have the values 1, 2, 3, 4, 5, and the number of pairs become 5. And when Q is equal to 10, P can have 1, 2, 3, 4, 5 and 6, and so the number of pairs are equal to 6. Now, when we add all these number of pairs, we get the total number of such pairs for which roots are non-real are 38. Also we see that total number of possible pairs are 10 into 10, as Q can have 10 values and P can have 10 values, so such pairs are 100. Thus the probability that the roots are real is equal to 1 minus 38 by 100. This is the probability that roots are non-real, and so we get the probability as equal to 0.62. So the final probability that the roots are real is 0.62. Let's see another solved example, and this appeared in ITJ in 1989, and it says that an unbiased coin is tossed. If the result is a head, a pair of unbiased dice is rolled and the number obtained by adding the numbers on the two faces is noted. If the result is a tail, a card from a well-shuffled pack of 11 cards numbered from 2, 3, 4 up to 12 is noted. Now what is the probability that the noted number is either a 7 or a 8? So in this problem we have been given that an unbiased coin is tossed. If the result is a head, then a pair of unbiased dice is rolled and the number obtained by adding the numbers on the two faces is noted. And if the result of tossing of coin is a tail, then a card from a well shuffled pack of 11 cards numbered from 2 to 12 is noted. We have to calculate the probability that the noted number is either 7 or 8. So one can get a 7 or 8 either if it appears a head on the coin and then the sum of the two numbers on the dice result in 7 or 8, or it appears a tail on the coin and then a 7 or 8 number card is picked from a well shuffled pack of cards. So we can have two possibilities. Either a head appears and then the sum of the two numbers on the dice results in 7 or 8, or it can appear a tail on tossing of coin and then a card is drawn which could be a 7 or 8 number card. So let us say that E1 is the event of getting a 7, E2 is the event of getting an 8, H is the event of getting a head, and T is the event of getting a tail. So we define E1 as the event of getting a 7, E2 as the event of getting an 8, H the event of getting a head, and T the event of getting a tail. Now, thus from total probability we get P of E1 equal to P of H into P of E1 by H plus P of T into P of E1 by T. This represents the probability of getting a 7. This represents the probability of getting a head. This represents the probability of getting a 7 when a heads has occurred. This represents the probability of getting a tail, and this represents the probability of getting a 7 when a tail occurs. Similarly, P of E2 would be P of H into P of E2 by H plus P of T into P of E2 by T. Again, this represents the probability of getting a head. This represents the probability of getting a 8 when a head occurs. This represents the probability of getting a tail, and this represents the probability of getting a 8 when a tail occurs. Now we know that P of H would be equal to P of T, and that is equal to 1 by 2. Either we can get a head or we can get a tail. Now, for getting a 7 on a dice, possible cases are 1, 6, 6, 1, 2, 5, 5, 2, 3, 4 and 4, 3. So P of E1 by H is equal to 6 by 36, which is equal to 1 by 6. The cases for getting a 7 numbered card is equal to 1. We have got 11 cards, and out of which there is only one card which is numbered 7. So P of E1 by T, that is the probability of getting a 7 when a tail has occurred, is equal to 1 by 11. Similarly, for getting a 8 on a dice, possible cases are 6, 2, 2, 6, 3, 5, 5, 3 and 4, 4. So we see that there are 5 cases. So P of E2 by H would be equal to 5 by 36. Similarly, cases for getting an 8 numbered card is equal to 1, as there is only one 8 numbered card from the pack of 11 cards. So P of E2 by T would be equal to 1 by 11. Thus P of E1 would be equal to, we put these values over here to get 1 by 2 into 1 by 6 plus 1 by 2 into 1 by 11. This is equal to 1 by 12 plus 1 by 22, and this is equal to 17 by 132. Thus the probability of getting a 7 is 17 by 132. Similarly, the probability of getting a 8 is equal to 1 by 2 into 5 by 6 plus 1 by 2 into 1 by 11, and that is equal to 91 by 729. Now we also see that E1 and E2 are mutually exclusive events, because if we get a 7 we cannot get a 8. Thus P of E1 or E2 is nothing but P of E1 union E2, and this is equal to P of E1 plus P of E2, which is 17 by 132 plus 91 by 792, and this is equal to 193 by 792. Thus the final probability of getting a 7 or a 8 is equal to 193 by 792. Now let's see the last solved problem, which appeared in IDJ 1991, and it says that in a test, an examinee either guesses or copies or knows the answer to a multiple choice question with 4 choices. The probability that he makes a guess is 1 by 3, and the probability that he copies the answer is 1 by 6. The probability that his answer is correct given that he copied it is 1 by 8. Find the probability that he knew the answer to the question given that he correctly answered it. Now in this problem we have been given that in a multiple choice question we have got 4 choices, and an examinee can either guess the answer, either he can copy the answer, or either he knows the answer to that multiple choice question. Now the probability that he makes a guess is 1 by 3. The probability that he copies the answer is 1 by 6. Also given to us is the probability that his answer is correct given that he copied it is 1 by 8. We have to find the probability that he knew the answer to the question given that he correctly answered it. Now this is an example where we use the Bayes theorem, but how? Let's check it out. Now this is any multiple choice question. Now there are 3 choices given to us. Either the examinee can guess it, the probability for which is equal to 1 by 3. Either he copies the answer and the probability for that is 1 by 6. Or the third option is he knows the answer to this question and the probability for which we do not know. So let us say that E1 represents the event that the examinee guesses the answer. E2 represents the event that the examinee copies the answer. E3 represents the event that the examinee knows the answer. And A represents that the examinee correctly answers a question. Also given to us is P of E1 equal to 1 by 3. P of E2 is equal to 1 by 6. So P of E3 would be equal to 1 minus 1 by 3 minus 1 by 6, which is equal to 1 by 2. As these are mutually exclusive events and they are also exhaustive events. So either the examinee can know the answer, either he can copy the answer, or either he can guess the answer. So that's why the probability of examinee knowing the answer would be equal to 1 minus 1 by 3 minus 1 by 6, and that would be equal to 1 by 2. Now the probability of the examinee correctly answering a question after guessing is 1 by 4. This is because we have got 4 options out of which he makes a wild guess. One of the option is correct, so the probability becomes 1 by 4. Thus P of A by E1 is equal to 1 by 4. This is the probability that he answers the question correctly and the condition is he guesses it. So this would be equal to 1 by 4. Also given in the problem is P of A by E2, that is the probability of answering the question correctly when he has copied it, is equal to 1 by 8. Also, we know that if the examinee knows the answer, then he would definitely answer it correct. He won't answer it wrong. So if any person knows the answer, he would definitely answer it correctly. Thus, the probability of answering the question correctly when he knows the answer is equal to 1. We have to find P of E3 by A. That is, he knows the answer for which he answered it correctly. Again, we are going to use the Bayes theorem for this. So P of E3 by A would be equal to P of E3 into P of A by E3 divided by P of E1 into P of A by E1 plus P of E2 into P of A by E2 plus P of E3 into P of A by E3. Thus this is equal to 1 by 2 into 1 divided by 1 by 3 into 1 by 4 plus 1 by 6 into 1 by 8 plus 1 by 2 into 1. So this is equal to 24 by 29. Probability that the examinee knew the answer given that he answered it correctly is equal to 24 by 29.